Okay, here is a very important section of linear algebra on systems of equations, and I'll just get right into it. There is a theorem involving systems of equations. There you see a system right there, which says that these 6 things are equivalent, which means they all live or die together. If one of them is true, all of them are true. If one of them is false, all of them are false. So they're all in the same boat, which is a very useful theorem, because if you want to prove any of them is true, all you have to do is to prove any of them and you get the others all for free. If you show that any of these things is not true, then you know they're all not true. This is the best kind of theorem in mathematics, okay? So let's take an example of a 3x3 system to illustrate how this works. Here's a system of 3 equations, 3 unknowns. Notice this is an n by n system, so it's 3 equations, 3 unknowns. I could write this as A being equal to the matrix 1, 2, 3, 2, 3, 5, 0, 1, 2. There's the matrix A. And then if I multiply it by the matrix x, y, z, that matrix, that product, has got to be equal to 3, 6, 1. Let me just verify that this is the case. Okay, we know how to multiply matrices now from the first video. So what are you going to get? This is a 3 by 3 multiplied by a 3 by 1. Which is going to give us, those two match up, it's going to give us a 3 by 1. Let's see once what happens if I multiply this out. 1x plus 2y plus 3z has to be equal to 3. Sure enough. Same thing here. 2x plus 3y plus 5z is 6, and so on. So you could think of this as the equation A. You could think of this thing here as being the vector x. And so if you write x with a vector on it, that means it's something that looks like this with an x, y, z. It's the solution, which has 3 components in this case. And then there's your variable, and then call this one b, and there's your b. So ax is equal to b is what that looks like. And in particular, this matrix A is a 3 by 3. So that's the kind of thing that we're dealing with here. Okay. So we'll come back to this later. Okay, so how do we go about solving this? If you remember from your algebra days, if you have systems of 3 equations, 3 unknowns, you can eliminate variables and eventually get down so that you find out what x is, and then you go back, and once you find x, then you can find maybe y, and once you find both x and y, then you can find z. And there's 3 things that you can do with those equations. I don't change the solution of this system at all if I just interchange the position of 2 equations, right? I can put this one on top and put this on the bottom. The solution set is the same. Another thing that doesn't change it is if I just take any equation and multiply it by a non-zero constant, then I haven't changed it. So if I change this to 2y plus 4z is equal to 2, it's the same plane. These are all planes in 3 space. It's the same plane. I've just changed the way the equation works. And then the final thing that you can do, which isn't quite as obvious, but it's also true, and it's what you did back in high school, is you can take any equation, multiply it by a constant, and then add that to another one. Remember, that's how you get rid of y's, for example. You multiply this by a -3 and add it here, and then you get rid of that one. And you can multiply it by -2 and add it there, and then you get rid of all the y's, that kind of stuff. So, so you can take any equation, multiply by a constant, and then add it to another equation and replace the original equation with that new one, and you haven't changed the solution set at all. Okay? So those are the 3 things. They're called row operations. Those are the 3 things we're going to do here. And instead of just doing it with all the x, y's, and z's, we're going to get rid of those, and you can tell where the x, y's, and the z's are. And so it's really the same thing, but it just makes it a little more slick by writing it without all the extra variables there. We see where they are. Okay, and so here's the process. It's called The Gaussian elimination is the fancy word for it. But what it effectively does is it says you start with your upper left-hand corner here, and you want to get a 1 there. Okay, so we already have a 1, so you don't have to worry. If you had a 5 there, we could divide everything by 5, or I could replace it with another row in order to get a 1 there. Once you get a 1 there, then you do what's necessary by way of multiplying and adding so that you get zeros all the way down below. So I zero out everything below. This is king, everything else is below. So now I've got a 1 there and zeros there. Now I continue going to the left until I get to something which is not a 0. Go as far to the left as I can until there's a non-zero there. And then I modify that to get a 1 there. Once I get a 1 there, then I get all zeros below it again. And I keep processing like that until wherever I end up with a 1, I have zeros all the way down below. So now I've got a upper triangular matrix because I have zeros all here. Once I have that, then I kind of go in reverse order. And these are all zeros now, so they're not going to mess me up. So now I can multiply these by whatever is needed in order to get zeros up above there. So you just watch as I do it now and see how this all works. So the first thing I'm going to do, I make a little thing like this. I'm going to leave this row just the way it sits. 1, 2, 3, 3. And now I'm going to multiply this row by -2 and add it to this one. -2 and add it gives me a 0 there. That's what I'm after. -2 times this and add it gives me a -1. -2 times this and add it gives me a -1 there. -2 times this and add it gives me a 0 there. Okay, I think I don't have all my hopefully I'm doing it right. Okay, then finally I'm going to I've got 0 here already, so I'll just leave this one just the way it sits. Okay, so I've succeeded. Now I want to get a 1 there. Well, that's easy enough to do. I'm going to do that without even taking a full step. I'm just going to multiply this row by -1. That gives me a positive there, and a positive 0. Okay, so now I've got that. Okay, so I continue this way. I've got a 1 here. Now I want to get zeros below it. So what do? I think I can squeeze one more in here. So it's going to be 1, 2, 3, 3, 0, 1, 1, 0. Leave that alone. Now, in order to get a 0 here, I'm going to have to multiply this by -1 and add it. So -1 and add it. Notice that's all 0. That's the way I wanted it. -1 and add it will give me a 0 here. -1 and add it will give me a 1 here. -1 and add it will give me a 1 there. Let me see if I have something similar to what I had before. Okay. I didn't finish this many steps, okay? Now what? Okay, now that I have 1s here and I have 0s below it, now I'm going to get 0s up above here. So I'm going to go like this. Okay, now I leave the bottom row alone. 0, 0, 1, 1. Okay, now to get I'm just thinking, does it make any difference which one I do first? No, I don't think so. I hadn't thought about this. To get a 1 here, well, I tell you what. Let's. I don't think it matters. Let's just go from right to left again. To get a 0 here, what do I have to do? I'm gonna leave this row alone. Okay, and now I'm going to multiply this row by -2 and add it. Agreed? If I multiply this row by -2 and add it, I'll get a 1 here. -2 and add it will give me a 0 there. That's what I'm after. And -2 and add it will give me a -2 and add it will give me a 1 right there. -2 and add it will keep me a 3 right there. Okay, everyone agree? And now finally, I can get zeros above this thing. And so I leave the bottom row alone. And now, what do? I take this row and multiply it by -1 and add it to this row. So watch what I do here. I take this row and multiply it by -1 and add it to this. So I'm going to get a 0, 0, -1 plus this is going to give me a 0. Oops, I'm sorry. I still have a 1 there. -1 times this and add it gives me a 0 there. That's what I want. -1 times this and add it gives me a -1. And now to get a 0 there, I do the same thing. -1 times this and add it. So I'm going to get a 1, 0. -1 and add it gives me a 0 there. -1 and add it will give me a 2 right there. See if I hopefully, yep, got the same thing as before. There it is. Okay, so this is the final form, which is what I want. And now I can read off what the solution is. What does this say the solution is? It says that x is equal to 2, y is equal to -1, and z is equal to 1. Okay? So now let's check to see what's true about this theorem. First of all, once I get it into this final form where I have it as simple as possible and basically have got it as close to an identity as possible, like I have here, if there are, by the time I get it in this form, which is called the row reduced echelon form, where I've made it as simple as possible, I count up the number of non-zero rows. How many non-zero rows do I have? 1, 2, 3, right there. 1, 2, 3. Don't worry about that. Just 1, 2, 3. There they are. And so notice that's what the rank is. The rank is the number of non-zero rows. Non-zero number of non-zero rows. That's when you've got it in this final form, okay? So notice that in this case, the number of non-zero rows is, this is a 3 by 3 system. The number of non-zero rows is 3, so that's true. Notice that I was able to convert this matrix to an identity matrix, so that is true. So the first one holds, the second one holds. The next thing is that when I solved it, notice that it solves to a unique solution. There is the one point in 3 space which satisfies these 3 equations. These are 3 planes that connect in 3 space. You can think of them as 2 planes with another plane coming right down the middle, and there's one point which is on those 3 planes, kind of like 3 points at the bottom of a room. Can you see up here? Here's 3 lines all coming together, 3 planes, this plane, this plane, this plane, they all come together at one point. So 3 planes come together at one point, there's a unique solution, okay? So that's true. This number 5 holds, okay? So this holds, this holds, this holds. Now, if instead of having 3, 6, 1 there, if I just had 0, 0, 0 there, then what would have happened? If I'd gone through these steps, all of this stuff would have ended up exactly the same, and these are just all zeros, so when I add them and multiply them and so on, I'm just going to end up with zeros. Do you see that? So if instead of setting it equal to 3, 6, 1, if I had set it equal to 0, 0, 0, then my final solution would have been x equals 0, y equals 0, and z equals 0. So that would have been the unique solution right there. So 4 holds, okay? So that one holds. Okay? Finally, I'm not going to do this because you already know how to do it, but you go ahead and find the determinant of this matrix. Okay? You know how to do this from the previous video. And you will find that that determinant is not equal to 0. Okay? I won't do it just to save time, but you go ahead and do it. Expand any way you want. over any row or column, and you'll find that that determinant is not equal to 0, so that one holds. And finally, the last thing, which, as I say, they're all either true or false, so apparently these are all true. The last thing which is the case is that this matrix has an inverse. Okay? So how do we find the inverse? We do exactly the same thing we just did. Sorry about this, I'm erasing all the evidence. But here's what we do. Instead of putting the answers here, 3, 6, 1, we put the identity matrix right here. 1, 0, 0, 0, 1, 0, 0, 0, 1. And we go through those same series of steps we did before, and we get this thing to look like the identity. And by getting this thing to look like the identity, whatever you do to this row, whatever you do to this part of the row, you have to do the same thing to this part of the row. So you just do it to the whole row at the same time. And by the time you're done, like the first thing would be to do what? Multiply this row by a -2 and add it to this row. So you're going to get rid of that, and you're going to end up with a -2 there, and so on. And so by the time you're done, here's what you end up with. You end up with -1, 1, -1, 4, -2, -1, -2, 1, 1. That's what you end up with. And it turns out that this thing right there is the inverse. So if this matrix right here, if we call this matrix A, then this matrix right here we call the inverse of A. We write it like that. And if you take this, you know how to multiply matrices now. Let me just make sure I gave you the right one. -1, 1, -1, 4, -2, -1, -2, 1, 1. Okay, yeah. So if you take these two and you multiply them in either order, you're going to get the identity matrix. And you should check this on your own. Don't take my word for it. You check it out. It gives you good practice multiplying matrices. And there you go. And there you get it. So that's the inverse. Okay? So, let me show you one other thing that's important here. Once you have the inverse, then let's think about how the inverse can be used. What did we say earlier? We said that if this is the matrix A, we said that A times X, where X is equal to XYZ, is equal to, in this case, it's, I'll just say B, and B is equal to, in this case, 3, 6, 1. Okay? So we know that this is true. So now look at what we can do with matrix multiplication. Remember what we learned in the first video? You can multiply both of these things by A inverse. Okay? And then I can reorder them. And then this thing gives me the identity matrix. And the identity matrix times anything just gives me X. The vector X. So what does that mean? That means that I could find the solution that I had before. I forgot what the solution was now. The solution was X was equal to XYZ was equal to, I've got it down here, 2, -1, 1. That's what we found as the solution. And so look at here. It says that I can find that solution by just taking the inverse and multiplying it by B. Okay, so in other words, all I have to do is take, I'm sorry now, well, let's see, I'm running out of room here. I should have thought this through more carefully. So X is going to be equal to, here it is right here, -1, 1, -1, 4, -2, -1, -2, 1, 1. And I multiply that, by b, which is your 3, 6, 1. And if I do that, I'm going to get my solution. And the solution is 2, negative 1, 1. And again, let's just do the first one. It's going to be negative 3 plus 6 is 3. 3 minus 1 is 2. And you can do the other two, and sure enough, you get it. Okay, let me make sure that you're still with me here. Okay, very good. Okay, so so the point is they all live or die together. Okay, so that's key. So it has all that stuff is true. Okay, so now let's do a different system. Okay, and this system is x plus 2y plus 3z equals 3, and 3x plus 2y plus z equals 5, and then y plus 2z equals 1. Okay, there's another system. Let's try the same thing with it. Okay, now I challenge you. See if you can do it ahead of me. So turn off the recording and try to do it on your own and see once if you can. If you can, it shows you're in good shape. Make sure I have that there. Okay, let's do it together. So, so notice the first thing to do is I got a 1 there. I'm going to get a 1 down below it. So I'm going to keep this the way it is. So I'll multiply this row by negative 3 and add it. That gives me a 0 there. Negative 3 and add it gives me a negative 4. Because negative 3 times that is negative 6. Plus negative 3 gives me a negative 8. Negative 3 and add it, let's see, is going to be a 4. Okay? And then I get 0, 1, 2, 1. See that? I'll leave that alone. So now I've got zeros there. Okay? Next thing, I'm going to get a 1 right here, and the way I'm going to get it is by, should I go ahead and do the step here? I guess I might as well. So I'm going to 1, 2, 3, 3. I'll divide all this by negative 4, so I'm going to get a 0, 1, 2, negative 1. Let's see, divide this, divide this, divide, let's see. So it's going to be, I got a mistake here, and I don't want to make a mistake. I don't want to, let's see. Let me just make sure. 1, 2, 3, 3, 2, 3, 1, 5, 0, 1, 2, 1. Okay, let me just make sure I did everything right. So this is right. I multiply by negative 3. Oh, negative 3 and add, it's going to be give me a negative 4 there. There we go. Negative 3 times this, now it gives me negative 4. There we go. Okay, so that's going to be a positive one. Thank you. Thank you. I could tell a bunch of you out there were yelling at me. Okay, and then this one stays the same. Like this. Okay, now what? Now we want to get a 0 there, so I multiply this by negative 1 and add it. So I get a 1, 2, 3, 3, 0, 1, 2, 1, and now when I take a negative 1 and add it, look at what happens. I get 0, 0, 0, 0. So that tells me that my 3 equations, my 3 planes, well, let's see what happens by the time we're done. Okay, so obviously I can't get it into an identity now because I don't have anything down here to turn into a 1. So my rank is going to be 2 rather than 3. See that? By the time I'm working on this, I have nothing here at all, just a row of zeros. So how many non-zero rows do I have? I just have 2 non-zero rows. Let's go ahead and finish it though. We'll take this, multiply by a -2 and add it here and see what we get. So the bottom row stays the same. Here's going to be 0, 1, 2, 1. And now I multiply this by a -2 and add it. -2 and add it gives me a 0 there. -2 and add it gives me a -1 there. -2 and add it gives me a 1 right there. Let me make sure I have the same thing I had before. Yeah, very good. Okay, so this is your final form. This is as simple as you can make it. And let's see what solutions we have to this system. Here's what you have. If you rewrite this out in terms of x, y, z now, you can write it as x plus, or x minus z rather, is equal to 1. And you can write it as y plus 2z is equal to 1. Agreed? This bottom row, there's nothing there. It's just saying 0x plus 0y plus 0z is equal to 0. So that's what we have. Now, what are all the solutions to this? Notice we have 2 equations with 3 unknowns. So we have some choices here. I can set z equal to any variable I want. Let's just set it equal to t. And if z is set, I could do it with any. I'll just choose z. I'll set z equal to t. And now that tells me that x is going to be equal, if I bring it over, it's going to be 1 plus z, so it's going to be 1 plus t. And notice that y is going to be 1 minus 2t. 1 minus 2t. Everyone agreed? Because z is equal to t. And so my x, y, z, what are all the solutions I have? Here's all my solutions. It's 1 plus t, 1 minus 2t, and t. Or I can write it like this. X, y, z is equal to, I can break this up and write it as t times the vector 1, -2, 1, and then I'm left with 1, 1, 0. Let me make sure it's the same thing I got before. Yeah. Okay, so this is super important. Look at all the things we learned from this. First of all, we have an infinite number of solutions because for every value of t, I've got myself another choice of x, y, z which satisfies this. If you think of this as being 3 planes, it's like 3 planes that all come together and form a line. There's a line between them. So you have an infinite number of solutions from those 3 planes, okay? And so that's the first thing to notice. Second, I guess another thing to notice is that, well, let's just go down this list. So since one of them failed, they all have to fail, okay? So first of all, the rank was not equal to n. That fails. I'll put an F there for fails. That fails. It could not be converted to I because we end up with a whole row of zeros there, so that failed. Okay? Since it couldn't be converted to I, there's no way that we could use the same procedure we had before to find an inverse. There is no inverse for it. There's nothing that when I multiply it by that, I'm going to get the identity matrix, so that's false. This thing here does not have a unique solution. It has an infinite number of solutions. So this one fails. If I had started by putting all zeros here instead, I would have gotten the same thing here, except these would have all just been zeros. You see that? These would have all been zeros. So instead of having this part, that would have been my solution. My solution would have been just that right there. So I still have an infinite number of solutions. I just don't have this part. So again, if you've watched some differential equations, you know that the solutions to differential equations involves finding the answer to the homogeneous problem when everything is set equal to 0, and then finding a particular solution. So that's exactly the same thing here we have here. We've got the homogeneous solution right here, which has infinite number of solutions, and then we have a particular solution for this thing. If you stick in 1, 0, 0 right here, notice what you get. 1, 1, 1, 0. If you get 1, 1, 0, you're going to get 3, 1, 1, 5, 1, 0, sure enough. So that's a particular solution. So all you need is you take the homogeneous plus the particular, and you have the general solution for this thing. But the point is, there's no unique solution for this either. Okay, so that's false too as well. Finally, if you were to find the determinant of this, and I'll let you do this on your own, you find the determinant of this matrix, you will find that that determinant is equal to 0. So that's true. And one reason you can tell it's equal to 0 is because you can change it into this matrix right here and this matrix right here. It's easy to see that the determinant of this matrix is going to be 0. And you can prove that if the determinant of this matrix is 0, then this one's got to be 0 as well. So that's all the case. Finally, if these numbers had been such so that the answer, if I had started off with maybe, I don't know, if I had started off with a 2 right here, I think that would have done it, then I would have ended up with something like this, like that. So if I would have started off with a different number here, I would have ended up with a different number here. Then look at what the situation is. 0x plus 0y plus 0z is equal to 1. There is no solution to that. It's like these two planes come together right here, and here's the other plane right there, and there's no solution on all 3 planes. It's like forming parallel lines. You've got 2 parallel lines, but you don't have any intersection. They don't intersect. So there's a case where you have no solutions. So this thing here says unique. If this is false, it could be false for 2 different reasons. Either it's because you have an infinite number of solutions, it's not unique, it's infinite, or it's because you have no solution. As I said, if you would have had a 1 here, you would have had no solution. So a unique solution means exactly 1 and only 1. If it's not unique, there's 2 ways to not be unique. It's either because you've got an infinite number of solutions or because you have no solution. Okay? So that's the most important thing to say there. I think that covers what I want to say here. You can also do this with 2x2 systems, and with 2x2 systems, it's again easy to kind of visualize. It's even easier to visualize if you have 2x2. Let's just spend a couple minutes with it here. If you have 2x2, then you can have this, for example. You can have 3x plus 5y is equal to 7, and x plus 2y is equal to 2. And if you put that into this form and do your row operations on it, you'll end up with this. Like that. And so there's a 2x2. It can be changed into an identity, and so there's a unique solution. And if you want to, you can find the inverse. Here's your A is equal to 3, 5, 1, 2. If you find the inverse of A, you'll find it is 2, -5, -1, 3. So you can do it the same way we did it before, but I will tell you something here which is kind of neat. You see a relationship between A and A inverse? The relationship is, to find the inverse for a 2x2, you take these 2 numbers and you switch them around. See that? 2 and the 3 are switched. And you take the negative of each of those. And there's one other thing you have to do. You have to divide by the determinant of A. Well, here I'll just say A. Here, let me just say this: if A if A is equal to A, B, C, D, then A inverse is equal to, what did I say? You flip the A and the D around, you take the negative of these, and then you divide the whole thing by the determinant of A. And the determinant of this one here, notice, is 6 minus 5 is 1. So that's why it turned out real nice. We didn't have any fractions there. Okay? So I think that is all I want to say. I'll just say by way of lines here, what are the different situations you can have with lines? I'll let you play with them. Here's a case where you had two lines that had a single point of intersection. If you choose two lines, I'll let you just play with this on your own. If you choose two lines that are parallel to each other, you play with it. You do it on your own. You take two lines that are parallel to each other, and you play with that, and you'll see that you get something with no solution. You'll get something like this, for example, whatever. And so there's no solution. Or if you have two lines that are basically right on top of each other, then again you'll get a situation like this, where you'll have something like 1, 2, 5, 0, 0, 0. So now you can do the same thing as before. You say that x plus 2y is equal to 5. So you can let your y be equal to t. And then your x is equal to negative 2t plus 5. And so what are all your solutions? X, y are going to be t times what? Negative 2 and 1 for y. And then what's left? 5, 0. So basically that happens when you have two lines that are just lying right on top of each other, and you're basically just getting that same line back again. Okay? So you play with a 2 by 2 if you want, but the 3 by 3 is kind of the more important one because it gets a little more interesting then. But all these same things, they either live or they die together. So I think that's all I want to say. Give me just a second. That should do it. The only other thing I had on my sheet here, which I've just mentioned to you, is that how did I come up with these these three systems of equations? I had 1, 2, 3, 3, 2, 1, 5, and 0, 1, 2. Oh, let's just make them all 0, 0, 0. Like that. Notice that if I take 3 times the vector 1, 2, 3, and I subtract 4 times the vector 0, 1, 2, I get the vector 3, 2, 1. If I take 3 times this one, subtract 4 times this one, I get this one. So that means that these three vectors are linearly dependent. Remember what it means to be linearly dependent? To be independent means the only way I can get one, I can't get one from the others. To be linearly independent means I can't get one from the others. To be linearly dependent means that this one is in the span of these, or this is in the span of those, or so on. So that's how I knew that this was going to give me basically a set of 3 planes that give me a line, because those three, they are linearly dependent. They have more than one point of intersection. Okay, very good. So that's a good review or introduction to systems of equations. Thank you.